This is Algebra 2 with Trig, 2A.2. We're going to analyze graphs of polynomials. What we're looking at is the zeros of the function and how that's going to flow through using our knowledge of end behavior. We have x, and x is going to be considered a solution. This is k, sorry. K is a solution. Now, it's weird using the letter k, but we're just talking about the value down here, x minus k. K, the number 2, is going to be a solution of the function. So if 2 is a solution, then you know that x minus k is going to be a factor. And you know that the k value is considered a 0 of the polynomial equation when f of x equals 0. If the k is a real number, then k comma 0 is an x-intercept. So this is relating back to everything that we've done before in quadratics. The same thing. We just now have more factors rather than just two terms. We're going to have, those aren't terms, but two factors. We're going to have more factors. In these cases, 3. If the factor is linear, we mean linear because this is x to the first power. This is a linear factor. This is a linear factor. That means each time it's going to be a single 0. That means the graph crosses the x-axis at the point K. Nothing different than what you've done before. So when we set this equal to 0, we say x minus 2 and x plus 1 and x plus 4. Those are all multiplying each other. This would be a cubic equation. If you multiply that all out, this would become cubic. You know that 2 binomials will multiply together to get x squared. And then when we multiply a third one into it, that's where you get your x cubed. This is a cubic. It has 3 different x factors. So we'll do our zero product property, setting each of our factors to 0. So x equals 2, x equals negative 1, and x equals negative 4. What that means is if you plug in one of these zeros, one of these solutions, into your equation, like you plug in a 2, you get 2 minus 2 is 0. 2 plus 1 is 3. 2 plus 4 is 6. So you get 6 times 3, that's 18. 18 times 0, that's why we're getting 0. It doesn't matter which one we plug in, it's going to make one of these zeros. So this is called the zero product property. And that's where the graph is going to cross the x-axis. Now we're going to use our end behavior. What do we know about a positive? See, there's like a 1 standing in front of here. That's a positive number. There's no negative sign. So this is a positive leading coefficient. If it's a positive leading coefficient, you know this is going to go in a positive direction. To the right, as x gets bigger, it's going to go in a positive direction because it has a positive leading coefficient. Because we have an odd degree, we have a 3, third degree. This is using yesterday's lesson. This is an odd degree. You know this is going to go in the opposite direction. Now, what do we do to get to the ends? How do we connect them? You definitely don't go straight across. Okay? But these are called single zeros. So that means they're going to go through each of the zeros as they work their way through to the end. We're not too concerned about how high we go or how low we go at this point. We're just given a sketch. The further the x-intercepts are apart from each other, the higher or further away from the x-axis it becomes. And in between these intercepts, it is not a perfect parabola. It is not symmetrical right down the center. That would make it really easy to find those maximum points. It's not a parabola. So it just works its way through. It goes all the way through. What's different about this equation? Seeing the square on this binomial tells us that this is different than this one. This one has 3 sets of parentheses. This one only has 2 sets of parentheses. Because right here, this is squared. You know that squared means you're going to write it twice. Now you have it 3 times, 3 parentheses. So you can identify that this is actually a cubic. Parenthesis times a parenthesis times a parenthesis is going to make it a cubic. Notice how this has a square there. This binomial is to the first power. You can add those together to see that it would be a cubic. Different ways to do that. So what we're noticing is that one of our factors is squared. That means it's going to be a double zero. The graph intersects the x-axis at this point. So we do our zero product property. X minus 2 equals 0, so x equals 2. X minus 2 equals 0, so x equals 2 again. That is your double zero. You got the same answer twice. You got x equals 2 times. That's because it's squared. You're going to have it twice. It's not a surprise. This one, x plus 1 equals 0, x equals negative 1. That's a single zero. Just like these were over here. That goes right through it. So we're going to plot the point of 2. We're going to plot the point of negative 1. We know that the leading coefficient is a positive. So that means the graph is going to go in a positive direction. We know that we have an odd degree. So in the other direction, it's going to be going opposite. They go in opposite directions because it's an odd degree, just like we learned yesterday. Now, can you envision how we're going to connect those dots together? Over here, we flowed right through it, and it worked its way right up. This one worked out really well. I can't go down and around. This is a double zero. What the double zero tells you is that the graph is going to bounce. right on that x-intercept. It bounces at the x-intercept of 2 because it is squared, because it is a double factor. Just like a parabola would have its vertex. If you had x minus 2, x minus 2, it would have a vertex right at positive 2. This is looking like the same thing. So how's this one going to be different? What do you see? Can you be observant to the way that it looks? This factor is cubed. The binomial is to the third power. That's cubed. It's known to be a triple zero. Why is it a triple zero? X minus 2, x minus 2, x minus 2, because it's cubed, it's going to be written 3 times. So you know your zeros are at 2, are at 2, are at 2. That means they're going to touch the x-axis at exactly 1 point. If I come over here and I graph out x cubed, you can see that I have x cubed. It's a positive leading coefficient, which means it increases. It's odd, that means it goes in the opposite direction. It curves up to that location and curves away. If I change my window so you can get in a little bit closer, it curves up to it and it curves away. A negative times a negative times a negative is still negative. Negative times a negative times a negative is still negative. 0 times 0 times 0 is now 0. Positive times positive times positive is now a positive. And it continues. So that's why it makes that curve. A half times a half times a half is only an eighth. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. Goes up really quick. And that's why you see it kind of spike so far up, because at 2 it has to be up here at 8. So that's what's happening. Well, we can use all our same rules that we've thought about before. This has a leading coefficient that's positive. So you know it's going to be increasing to the right. You know that it's an odd degree. So you know it's going to go in the opposite direction. This way. That's really the lesson. Everything else is going to be doing practice problems of just those. Okay, multiplicity. Refers to the number of times the zero associated factor appears in the polynomial. So if you notice that this is a square, the multiplicity of this factor is 2. We look here and we see the degree is going to be 3, but maybe more importantly, it is odd. It's an odd degree. We know that the leading coefficient is a negative. So we can do our end behavior. We don't even need to see what the graph looks like. We definitely don't need to use our calculator. Because this is a negative leading coefficient, you know the graph is going to be going down in the beginning. Or down as x gets bigger. And because it's an odd degree, you know that the graph is going to be going in the opposite direction. That's the lesson we had yesterday. The negatives, as x gets bigger, it goes down. Odd, it goes in the opposite direction. So we know our zeros are going to be at -2 and that equals +1. Now I'm going to write this one twice to help remind myself that this is a double zero. I'm being observant that this is a double zero. So I'm crossing at +1 and I'm crossing at -2. I know that it's negative, so it's going to fall to the right. I know that it's an odd, so it's increasing to the left. It's going in the opposite direction. Now what's going to happen in between? It's going to bounce at 1. Some people say, how do you know if it bounces up or if it bounces down? Well, if the graph has to go down because of the negative, then it has to bounce in a downwards action. And then we have to curve back up to reach this other zero. It doesn't bounce here because at -2 we have a single zero. It goes right through it. In the next one, I notice there are 3 zeros, or 3 factors. So this is an odd degree again. The leading coefficient, you see the 0.25. That's pretty irrelevant to what we're doing. We're not paying attention to the 0.25. We're paying attention to that it is positive. That's what you've got to realize. So now we know we have a 0 at -2, a 0 at 1, and a 0 at 3. So I'm crossing at -2, +1, and +3. What does my positive leading coefficient tell me? That it increases to the right. The odd tells me that it goes in the opposite direction to the left. You could probably just use your eyes here. It has to flow all the way through. There's no other way to get from point A to point B. They're all single zeros. There's no double zeros. There's no bouncing here. They're all separate. It doesn't matter how far down you go or how far up you go, but be sure you get away from the x-axis. Don't go straight across. Take your time, make it flow through here nicely. Do the best you can to not have x values repeat each other. So don't mistakenly curve back across to whip way over here. You don't want them underneath each other. That wouldn't be a function. Here we do the same thing again. But what's different about this one? What do you see? You got to be observant. I see a square and I see 3 terms, but this is a square. So I know this is the 4th degree. This is going to be even. My leading coefficient is going to be a positive. I know I'm going to have a 0 at -3. I know I'm going to have a 0 at 4. I'm going to have another 0 at 4 because that's a double 0. Because it's squared. There's 2 of them. and then 1. You know your end behavior. As x approaches negative infinity, the function is going to approach something. And as x goes to the right, you know the function is going to approach something. Because the leading coefficient is positive, you know it's going to be going up as x gets bigger. That's this way. And because it's even, you know that it's going to be going in the same direction, which is that way. But what happens in the middle? At -3, it goes right through it. At +1, it's not in that same order, but that doesn't matter. At +1, it goes right through it. So this gives us the hint that at +4, it must be doing something so it can go back up. That's because it's a double zero. And that worked out great. So same thing we were doing before, just now with more factors. You can do that with any number. Many polynomial functions do not have a maximum value. This does not have a maximum value because it goes up in both directions. It goes up, you never hit a maximum. And the same thing would be if it was going down, you never have a minimum. It doesn't have a max, it doesn't have a minimum. But we can talk about local maximum and local minimum. Those are where the graph looks to be going at the highest point. That's a local maximum. This would be a local minimum. These are the y values of the turning points. The points are all higher or lower, depending on how you're looking at it. All the points around this maximum are lower than it. So that means, since it's the highest point from anything around it, it's called a local maximum. This location here is lower than any other point around it, so it's considered a local minimum. The graph of every polynomial of n degree has n minus 1 turning points. What that means is that when we have a parabola has 1 turning point. This is y equals x squared of some type. You could call it x plus 2, x minus 3. It's a second degree. It's going to occur, but the main thing we're focusing on is 1 turning point for a square. A cubic. We could call this one x plus 5. This is really close to x, so we often put that in front. And then x minus 4. That would be a cubic equation, crossing at -5, at +4, and at 0. But what we're discussing here is the number of turning points. A cubic can have 2 turning points. Let's use x again, because that's a good lesson. X plus 4, that's going to cross out here. X means they're going to cross at 0. X minus 1, x minus 3. If I had a negative in front, doesn't matter. 1, 2, 3, 4. 4 of those, you know it's going to be going down because of the negative. It's going to be going down because of the odd degree, or even degree goes in the same direction, my bad. But what I want to show you is that fourth degree has 3 turning points. It always has n minus 1 turning points. 1 less than the degree. The polynomial has n distinct zeros. So if it has 2 distinct zeros, the number of turning points is going to be 1 less than that. 3 distinct zeros is going to be, the turning points is 1 less than that. So it has n minus 1 turning points. This is the 5th degree. So how many turning points could it have? Fifth degree will have up to n minus 1, which is 5 minus 1, which is 4 turning points. 4 answers the question. How many turning points would it have? It would be 1 less than the degree. Estimate the coordinates of each turning point. We're just estimating them. We're just using our eyes, trying to see whereabouts, what are we talking about. A turning point is the y value. These are the y coordinates of the turning points. Well, here's a turning point. That's up at 1, 2, 3, 4 and a teeny bit extra. So that would be 4 and a little bit extra. We have a local minimum over here. That's a local min. This is a local max. So the local min is just a little bit less than 0. The zeros themselves, this looks to be negative 1.8. This looks to be almost exactly at 1. This one looks to be a little bit less than 0, or actually 2. The 0 is less than 2. And so we'll call it 1.9. So based on the given graph, the polynomial has at least 1, 2, 3. It's a degree of 3. The turning points are 2. 1 less than the degree is the number of turning points. We say it's at least the degree of 3 because it could actually be 5. It's possible to make a 5 look a little bit like this, but this is so smooth going through the curves that I'm pretty confident it's a cubic. If it had some distortion, it doesn't flow straight through. It wiggled a little bit more throughout. That you might expect it to be 5, but this is going to be 3.